Hi, my name is Georgi Duf and I would like to talk about high-speed comparators. What does determine the speed and gain of a comparator? I will analyze the relationship between speed and gain of the core of the comparator, the latch, and I will establish its dependencies on the design parameters of the latch, the equivalent capacitance, and the equivalent GM. A comparator is a single-bit digital-to-analog converter. It compares a signal against a reference and it outputs single-bit information which is bigger. The simplest case is when the reference is 0. Then we compare the signal against 0 and we say either it's positive or negative. You can draw simple characteristic of the comparator as shown in the graph. For all negative inputs, the output will be the output of the comparator will be voltage low, and for all positive inputs, the output of the comparator will be voltage high. Now, if you don't have that much time and you want to force decision of the comparator, for very small input signals, the comparator will not have time to settle completely to voltage high or voltage low. So there will be a certain region, which we call a metastability region, for which the comparator cannot take a full-fledged decision, voltage low or voltage high. And this region will depend on the input signal. The smaller the input signal is, the smaller the output voltage of the comparator will be. The slope that results from the input-output relationship for a given time at high speed determines the gain of the comparator. There are many different implementations of a comparator, but usually the comparators are differential circuits. So the output is available as output positive and output negative voltage. The input is also differential, input positive and input negative. You can use, for example, one of the inputs as the reference and the other for the signal, or you can connect directly the differential input and then assume that the reference is 0. There are different architectures of the comparator, and they have, however, many things in common. To generate a lot of gain, they will use a latch, which is a positive loop of two inverters. They will use a reset circuit to break the latch decision, the latch lock, and create a new and make a new comparison, and they will have possibly some preamplification for the input signal. So you can distinguish in the different topologies of the comparator these three main functions. And usually you have such an output characteristic seen in time for the comparison cycle of the output nodes, output P and output N. You have a certain period which is the reset period, where you break the positive loop of the latch and you prepare the latch to take a decision. Then you sample the input signal, and what you can see is that the output signals usually settle to a common mode level. Then you have the regeneration phase, where the latch works and its positive feedback lock works to settle the outputs to the correct values. Once the outputs separate, they will settle to the VDD and ground, the supply rails, and you can sample then the output of the comparator. This will be the 1-bit information that you have for the comparison, and then you go to the reset phase in order to prepare the comparator for a new decision. Now in these phases of the comparator settling, usually the reset phase and the common mode settling and the slew phase are very much controllable. They're predictable. The regeneration phase depends on the size of the input signal. If the input signal is very small, the regeneration phase will take usually longer time. If the input signal is large, the regeneration time will take less time. So the regeneration time depends on the implementation of the latch. And the latch is the positive feedback that exists between these inverters. And this is what we'll analyze. And this is an example of a latch, a very popular example. This circuit is used often. Two inverters, CMOS inverters, that are locked in a positive feedback. The input of one is the output of the other and vice versa. So we have two signals, the signal node X and the signal node Y. And we can draw the input-output characteristic of one of the inverters. And for the other, we need only to rotate the characteristics, since the output of the first inverter is the input of the second inverter, and the output of the second inverter is the input of the first inverter. So the solution for the settling of the signals X and Y will be the crossing point of the two transfer characteristics. And the transfer characteristics of the two inverters cross at 3 points. 2 points on the corners, which we call the stable points, and 1 point in the middle, which we call the metastability point. We call it metastability point because the slightest deviation from this equilibrium will activate a positive feedback between the inverters and resulting chain reaction, which will lead the outputs to settle to one of the two stable points. So for X, for example, either VDD or ground, and for Y, either ground or VDD. Now, this process from metastable point to a stable point is actually the regeneration of the latch. And we will investigate what is exactly the analytical function that governs the settling and what it depends on in terms of circuit parameters. Because ultimately this will determine the time and gain of the comparator. Now, how we can analyze this circuit? For the model of the inverter, we'll use a single pole amplifier, which models the two transistors with an equivalent GM, transconductance stage. This is a voltage dependent signal source. And let's say that for one stage we have GM, then the current source will be GM X, and the other current source will be GM times Y, where X and Y are the voltages of the two nodes X and Y. Then we can also model the output resistance of the transistors. This is the channel length modulation effect as an equivalent resistor to ground. For this particular circuit, it will be, of course, the output resistance of the NMOS transistor in parallel with the output resistance of the PMOS transistor. And then we can also model from node X and Y an equivalent capacitance to ground, where the equivalent capacitance to ground will be the sum of all capacitances that are between nodes X and Y. So you can think about gate source capacitances of the NMOS transistors, gate source capacitances of the PMOS transistors, gate drain capacitances of the PMOS and the NMOS. So you can group all these capacitances in one equivalent capacitance that can be modeled from node X and Y to ground. Now, of course, the comparators, the inverters are balanced, so we can draw two equivalent circuits for the single pole model that consist of voltage dependent current source, equivalent capacitance, and equivalent resistors in parallel, and then another group of voltage dependent current source, equivalent capacitance, equivalent resistance. The capacitances and the resistances, of course, are the same, so because we have a balanced circuit, and then the only difference of the two parts are the voltages X and Y, and the current sources which depend on the other voltage X, and the other current source depends on the voltage Y. So now to analyze this circuit, we will write the Kirchhoff current law for the two nodes X and Y, and the Kirchhoff current law requires that the sum of all currents are equal to 0. So the current of the voltage dependent current source plus the current that flows through the capacitor plus the current that flows through the resistor is equal to 0. We have two groups of the circuit, and then we have hence two equations. We subtract the two equations to get a third equation, which will be the difference of both equations, and we have Gm times the difference of the two voltages, and then see the derivative of the difference of the voltages with the opposite signs, and the opposite of the and the difference of the voltage divided by the resistor. Now the difference of the voltages we defined as delta V, and of course y minus x is defined as delta V, then x minus y will be minus delta V. So we rewrite the equation, and then we can group variables, and we get a simple differential equation. We can simplify further by realizing that Gm is usually much larger than 1 over R. Keep in mind that R is the channel-length modulation effect, and it models the output resistances of the NMOS and the PMOS transistors. So we can for the sake of simplicity, we can simplify the equation further by ignoring 1 over R. Now, this is a simple differential equation, linear differential equation, and the solution is of this form, that delta V, or the voltage difference between the output, between the two nodes of the latch, is in time. Is an exponential function, which depends on a constant k, and then the exponential function depends on Gm divided by c times t. So the first thing that we see is that if t goes to infinity, then delta V will go to infinity. And this is, of course, eventually to settle to ground and VDD. But this is what we expected from the beginning, that given sufficient time, the output of the comparator will settle to the VDD and ground. Now, what is K? And K can be derived by the boundary conditions. So what we know is that at time 0, then the exponential part will be 1, and then K will be simply delta V. And this is actually the input voltage of the comparator, delta V in. So we assume that we start at the metastable point, and then we require a little bit of unbalance, or the initial conditions, or input voltage, delta V in, to activate the positive feedback of the latch. So K now, then, this coefficient of the differential equation, is the input voltage. Then at T1, or T1 is the time given to the latch to settle, to regenerate its output, then the output will be simply delta V in times the exponent of Gm divided by C times T, and this will be the output voltage. So now we can define the gain of the latch as the ratio between the output voltage divided by the input voltage, and it will be simply the exponential function, which is a positive exponent of the time constant Gm divided by C, and of course times T. The more time we have, the higher the gain. But if the time is fixed, then the gain depends on the Gm and the C, and the Gm is the equivalent gain that we have in the latch loop, and C is the equivalent capacitance that we have in the latch loop. Now you can see that the more gain you have in the loop, the more Gm that you have from the transistors, the more gain you have, the higher the gain of the latch. the less capacitance, parasitic capacitance you have in the loop, the more gain you have in the latch. And there are different transistor level implementation, realization of the latch. Here I give two examples which are often seen in the implementation. On the left side you have an inverter realized common source transistor with PMOS load, and on the other side you have the inverter realized as NMOS and PMOS transistors. So you see that in one case you have more capacitance. You have more capacitance because you have the capacitance of the both NMOS and PMOS transistors, and in the other case you have less capacitance, equivalent capacitance, because you have only the capacitance of the NMOS transistors, and from the PMOS you consider only the gate drain capacitance, but not the gate source capacitance. However, for the equivalent GM, you also have differences. In one case, the equivalent GM will be the sum of GMN and GMP, the GM of both transistors, NMOS and PMOS transistor, and in the other case, the equivalent GM that you have will be only given by the GM of the NMOS transistors, so you have less GM. So which one is faster and delivers more gain? It depends on the actual technology and the sizing of the transistors and the design of the latch. So there is always a trade-off and optimization. So what we consider so far is that the regeneration phase is controlled by an exponential function that depends on the time constant of the latch and the time constant of the latch is GM divided by C, where GM is the equivalent GM of the inverting stage, and C is the equivalent capacitance of this inverting stage.